Hello friends, welcome back to my YouTube channel. From this video lecture, I will start my discussion on mass transfer coefficients, and this would be part number 1 of that discussion. So this is mass transfer coefficients part 1, and in this video lecture, I will be introducing mass transfer by turbulent diffusion to you. So this would be an introductory lecture on mass transfer by turbulent diffusion. I have completed my discussion on mass transfer by molecular diffusion. Now from this video lecture, I will start discussing mass transfer by turbulent diffusion. And the rate of mass transfer in turbulent diffusion, it is described in terms of mass transfer coefficients. So that's why I'm giving title mass transfer coefficients to this discussion. So in part number 1, I will introduce turbulent diffusion to you. So at the end of this discussion, you'll understand how mass transfer takes place by turbulent diffusion. So let us start the discussion. Okay, to begin with, we will understand or we will know what are the limitations of molecular diffusion. So let me tell you, in industrial mass transfer operations, turbulent diffusion is always preferred over molecular diffusion. Molecular diffusion is not preferred. Turbulent diffusion is preferred. Why? Because there are certain limitations associated with molecular diffusion. Now let us know what are these limitations. First limitation is mass transfer by molecular diffusion. It is a slow process. So therefore, mass transfer rates are low. Mass transfer by molecular diffusion is a slow process. That is the biggest limitation associated with molecular diffusion. So in molecular diffusion, we know there is transfer of a substance through another substance from a place of high concentration to a place of low concentration by the movement of individual molecules. So mass transfer by molecular diffusion, it happens due to movement of individual molecules. And why are these molecules moving? The molecules move as they possess thermal energy, but their movement is very slow. That's why mass transfer by molecular diffusion, it is a slow process. The driving force for mass transfer is concentration gradient. That means the transfer continues till the concentration of the diffusing substance becomes uniform. So as long as there is concentration gradient, the transfer of the substance will continue. Once concentration gradient becomes zero, mass transfer by molecular diffusion, it will stop. So molecular diffusion, mass transfer by molecular diffusion, it continues as long as there is concentration gradient. Then second limitation is molecular diffusion is predominant only in the following cases. Which cases? In stagnant fluids and in those fluids which are flowing under laminar conditions. But both the cases, they are not preferred. They are generally not preferred in industrial mass transfer operations. We don't need stagnant fluids in industrial mass transfer operations. We don't need fluids that flow under laminar conditions in industrial mass transfer operations. What is required? We need we need fluids that are flowing under turbulent conditions. We need turbulent conditions in fluids. So this will always give high mass transfer rates. Mass transfer will be rapid. But this is not possible with molecular diffusion. This is not possible with mass transfer by molecular diffusion, and that is the second limitation. Let us move ahead. Then third limitation is mass transfer by molecular diffusion. It is limited by concentration gradient. So as I said earlier, mass transfer by molecular diffusion, it will continue to happen as long as there is concentration gradient. Once concentration gradient becomes zero, mass transfer will stop. So that's why we are saying mass transfer by molecular diffusion, it is limited by concentration gradient. So mass transfer will continue as long as the concentration gradient exists. When the concentration gradient when the concentration gradient is small, the rate of diffusion is also, or the rate of molecular diffusion is low. So when the concentration gradient is small, and as it becomes smaller and smaller, the rate of diffusion will also become lower and lower. Then the other limitation is mass transfer by molecular diffusion. It is limited by physical properties of the diffusing substance. Which are these physical properties? So molecular diffusion in gases, it is faster than in solids and liquids. Further, molecular diffusion in liquids, it is faster than that in solids. And molecular diffusion in solids, it is extremely slow. So mass transfer by molecular diffusion, it is also limited by the physical properties of the diffusing substance. If the diffusing substance is a gas, then molecular diffusion will be fast. If it is liquid, it will be slower than gas, but it will be faster than in solids. And in the case of solids, molecular diffusion, mass transfer by molecular diffusion, it is extremely slow. So the limitation is mass transfer by molecular diffusion. It is limited by the physical properties of the diffusing substance. In gases, molecular diffusion is faster, and in solids, molecular diffusion is extremely slow. Let us move on. Then the other limitation is mass transfer by molecular diffusion is limited by temperature and pressure. That is, molecular diffusion, it depends on temperature and pressure. So for gases, the diffusion coefficients which describes the ability of the substance to get transferred by molecular diffusion. So for gases, diffusion coefficients are affected by temperature and pressure. So when temperature and diffusion coefficients for gases, they are directly proportional to T raised to some power, and they are inversely proportional to pressure. I have discussed this in my discussion on diffusion coefficients. So for gases, the diffusion coefficients, they are affected by temperature and pressure. And for liquids, the diffusion coefficients, they are affected by temperature. So temperature and pressure, they also act as limiting factor in the case of molecular diffusion. So that's why we are saying mass transfer by molecular diffusion, it is limited by temperature and pressure. High diffusional rates, they are obtained at high temperatures. So because in both the cases, that is molecular diffusion in gases and then molecular diffusion in liquids, the diffusion coefficients, they are directly proportional to temperatures. So that's why high diffusional, you will be able to get high diffusional rates at high temperatures. Then the other limitation is mass transfer only by molecular diffusion is not sufficient in industrial equipment. So as we understood earlier, molecular diffusion is generally not preferred. Molecular diffusion alone, it is not preferred in industrial mass transfer operations. We need it in combination with turbulent diffusion, which we are going to understand. Turbulent diffusion should be dominant. That is the requirement. So mass transfer only by molecular diffusion, it is not sufficient in industrial equipment. So that is another limitation. So for example, distillation columns, reactors, absorption columns, etc. So these are various mass transfer equipment, industrial mass transfer equipment, and we need turbulent conditions in this equipment. That's why only molecular diffusion, it is not desirable, it is not preferred in these equipments. Now, after knowing what are the limitations with molecular diffusion, let us understand why there is need for turbulent conditions in those mass transfer equipment or in industrial mass transfer operations. Why turbulent conditions are preferred. So in mass transfer operations, turbulent conditions, they are always preferred. This is the first thing that we need to understand. So why they are preferred? Because under turbulent conditions, we get high mass transfer rates under turbulent conditions. So turbulent conditions are always preferred, as high mass transfer rates, they are obtained under these conditions. Therefore, a majority of mass transfer equipment that are used in industry, they are designed to have turbulent conditions. So at the design stage itself, care is taken that during the actual operation, turbulent conditions will be created and we will be getting high mass transfer rates in those equipment. So in majority of mass transfer equipment, they are designed to have turbulent conditions in them. But in all of this equipment, even though we have those equipments designed to have turbulent conditions, but in all those equipment, there are regions where fluids remain stagnant, or fluids remain under laminar conditions. So, but in all of these equipments, there are few stagnant regions where conditions are laminar. So, even though in the bulk you have turbulent conditions, but there are few stagnant regions where laminar conditions prevail. So, for example, if you take example of a CSTR, you can find stagnant regions in the corners of the tank, and then you can find stagnant regions near the tank bottom and even behind baffles. So in these regions where fluid remains stagnant, laminar conditions will be prevailing, and over these places, molecular diffusion will be predominant. It will be predominant only in those places where stagnant conditions are prevailing or where laminar conditions are prevailing. So in every equipment, you have such few stagnant regions where conditions remain laminar and you have molecular diffusion dominant at those places. Let us move on. So right now we understood what are the limitations of molecular diffusion, and then why there is a need for turbulent diffusion, why there is a need for creating turbulence during mass transfer operations. Now let us understand what is turbulent diffusion. A fluid, it could be a gas or a liquid, in a turbulent motion, when a fluid, either gas or liquid, is flowing under turbulent conditions, then this fluid is characterized by the presence of circulating or eddy currents. So when there is turbulence within a fluid, there are circulating or eddy currents. And these eddy currents, what do? They are responsible for fluid mixing. This eddy currents brings about mixing of the fluid. And this fluid mixing, in the presence of concentration gradient, when there is mixing of fluids, when chunks of fluids mix with each other due to turbulence, and there is concentration gradient, this combination will result in transfer of the substance which has the concentration gradient. So fluid mixing due to eddy currents under turbulent conditions plus concentration gradient of a substance will bring about its transfer. So as the eddies will be moving from eddies or large chunks of fluid, they will be moving randomly within the fluid when the fluid is under turbulent conditions. And along with their movement, the substance present in the fluid, it will be getting transferred. So here there is transfer of substance which is happening due to movement of EDs. And such a transfer is nothing but turbulent diffusion. So this fluid mixing, which is due to ED currents in the presence of concentration gradient, brings about the transfer of the substance which has a concentration gradient. So therefore, you can define turbulent diffusion in a simple way. Therefore, turbulent diffusion is defined as the rapid transfer of mass that is brought about by ED currents in a fluid under turbulent conditions. This is turbulent diffusion. Rapid transfer of mass that is brought about by ED currents in a fluid that is under turbulent conditions. This is turbulent diffusion. So molecular diffusion, it is due to movement of individual molecules, whereas turbulent diffusion, it is due to movement of EDs, large chunks of fluids, which randomly move within the fluid that is under turbulent conditions. And along with this movement, substances get transferred. And this transfer is nothing but turbulent diffusion. Let us move ahead. So let us understand it with a simple schematic diagram. So you have a tank and there are two substances. So let us say a substance with green molecules and substance with white molecules. And if an agitator is introduced into the tank, it is rotated. Then due to this rotation, due to this agitation, turbulence will be created. There will be formation of EDs and this EDs, it will result in the transfer of these substances. So the substance with green molecules will be moving from a place of high concentration to a place of low concentration. And this movement, it will be brought about along with the movement of the EDs that are formed within this liquid. Why there is formation of EDs? Due to the turbulence that is created by agitation. So in this way, turbulent diffusion is brought about by movement of EDs that are formed under turbulent conditions. So as the EDs move randomly, they will be carrying the substance along with them. And it will bring about the transfer of that substance. So in this way, mass transfer takes place under turbulent conditions, and we call that as turbulent diffusion. Turbulent diffusion, it is also called ED diffusion. So let me just write over here. Turbulent diffusion, it is also called ED diffusion. The other name is ED diffusion. Why ED diffusion? Because it is due to the movement of EDs. So I hope the concept is clear to you. You must have understood what is the difference between molecular diffusion and turbulent diffusion. Now, under turbulent conditions, where you have EDs, circulating currents within the fluid. So under turbulent conditions, what happens? Those fluid particles will no longer move in orderly manner as they move under laminar conditions. So under turbulent conditions, fluid particles do not move in an orderly manner as they do under laminar conditions. Instead of that, EDs or chunks of fluid, they move rapidly in a random manner. So this blue color EDs that I have shown over here, they are moving rapidly and in a random manner. So instead of orderly movement of individual molecules, which happens under laminar conditions, under turbulent conditions, there are EDs or chunks of fluid that move rapidly in a random manner. So EDs or chunks of fluid, they contain the substances that are present in the fluid. So whatever substances are present, they will be contained in those EDs or chunks of fluid. And as EDs move rapidly from one part of the fluid to the other, they bring about the transfer of the substances. And this transfer is mass transfer by turbulent diffusion. So I hope the concept is clear to you. If you have any doubts, you please mention that in the comment section. Let us move ahead. Then let us say that you have a pool of water. Now in this schematic that I have shown over here, I have shown pool of water which is almost stagnant, or laminar conditions are prevailing in this pool of water. And this white color, white color moving block, it shows turbulent, the movement of flow or the flow of air under turbulent conditions. So what I want to show over here is, air is moving under turbulent condition past a stagnant pool of water. This is one situation. The other situation is, let us say that there is a solid wall and liquid is flowing under turbulent condition along this wall. Two situations where the fluid is under turbulent conditions. So here air is under turbulent condition, over here in some liquid is under turbulent conditions. Now let us understand what happens in this situation. So now let me talk about these two situations. So this is water. Let it be A. So when air comes in contact with this water, what is going to happen? Water will evaporate into the air. And once water vapor enters the air, they will be diffusing through it. And air is under turbulent conditions, so there will be turbulent diffusion. So air. Now in this, even though air is moving under turbulent condition, very close to the surface of water, there is a thin film of air. And why it is different than the bulk of the air? Because in this thin film, which is close to the surface of water, conditions are laminar. And in these laminar conditions, molecular diffusion will be predominant. That is, within this film, molecular diffusion will be predominant. And as you move away from the surface, in the bulk of the air, turbulent conditions will be, there will be turbulent conditions. So as you move away from the surface, conditions will become turbulent. At the surface, you have a film where conditions are laminar within the film, but as you move away from the surface, conditions become more and more turbulent. And in those turbulent regions, turbulent diffusion will be prevailing, whereas within the film, molecular diffusion will be predominant. The same is the understanding in this example. You have solid A, where liquid is flowing under turbulent conditions. Then very close to the solid surface, there will be a thin film where conditions will be laminar. And when you move away from the surface, conditions will become turbulent. So within the film, you have molecular diffusion, the dominating phenomenon. But as you move away from the surface, turbulent diffusion will be becoming the dominant phenomenon. So in this way, when you have such situations, then you are moving from a place where place that is close to the surface, where molecular diffusion is predominant, and as you move away from the surface, turbulent conditions will become, or turbulent diffusion will become predominant. So let us understand. Now in this case, the concentration gradient, most of the concentration gradient, it will be lying within the film. Most of the concentration gradient, it will be lying within the film. I will show that with the help of a simple graph. So let us move ahead. I hope you have understood these two situations. That means when one fluid is flowing under turbulent conditions, whereas the other one is stagnant, then you have molecular diffusion. You have laminar conditions close to the surface, but as you move away from the surface, turbulent conditions become predominant. So let us move on. So as I was talking about the concentration, so if you plot distance z, which is distance from the surface, so let me just show. I had shown a pool of water and air was flowing past this pool of water, and now we are talking about distance z from the surface. So if you plot that distance on the x-axis and concentration of E in the film, concentration of E in the fluid or in the air in this case, then the concentration, it will change in this way. So most of the concentration gradient, it will be lying within the film that I have shown just now. So within the film, most of the concentration gradient will be existing, and when you go in the turbulent condition, the concentration gradient, it will become smaller and smaller. So that means as you move away from the surface, the concentration gradient becomes smaller. Most of the concentration gradient, it is lying within the film. So I hope this is clear to you. So that means when you have a stagnant film at the surface, then most of the concentration gradient will be existing in that film. Let us move on. Then finally, I will compare molecular diffusion with turbulent diffusion. It's a very important topic. You need to know what is the difference between molecular diffusion and turbulent diffusion, or you should be able to compare molecular diffusion with turbulent diffusion. So let us understand. So we will write points for molecular diffusion, and then we will write corresponding points for turbulent diffusion. Now, first point under molecular diffusion. Molecular diffusion, it is due to the movement of individual molecules under the influence of concentration gradient. What is the corresponding point under turbulent diffusion? Turbulent diffusion, it is due to rapid movement of EDs in a fluid under turbulent conditions. So it is due to rapid movement of EDs, and molecular diffusion, it is due to movement of individual molecules due to their thermal energies under the influence of concentration gradient. Then in molecular diffusion, the individual molecules, they are moving due to their thermal energies, as I said, whereas in turbulent diffusion, the EDs are moving due to convective flow. And why convective flow comes into picture? Convective flow results due to the movement of EDs. So here the movement of EDs is due to convective flow. The movement of EDs results in a convective flow, which brings about the transfer. Then in molecular diffusion, fluid particles move in an orderly manner, whereas in turbulent diffusion, there is no orderly movements. Instead of that, you have rapid and random movements of EDs. No orderly movement during turbulent diffusion. Whereas in molecular diffusion, fluid particles move in an orderly manner. Then molecular diffusion, it is a very slow process, whereas turbulent diffusion, it is a very fast process. Let us move on. Then molecular diffusion, it will continue till uniformity in concentration is achieved. But turbulent diffusion, it will continue till there is convective flow. So if convective flow stops, turbulent diffusion is going to stop. But molecular diffusion will continue. Turbulent diffusion continues till there is convective flow, but the final uniformity in concentration is achieved by molecular diffusion. So once the convective flow stops, turbulent diffusion stops, but molecular diffusion will continue, and it will continue as long as there is uniformity in concentration. So molecular diffusion, it will continue till concentration gradient becomes 0 or concentration becomes uniform. Turbulent diffusion will stop once the convective flow is stopped, but molecular diffusion will continue until there is a concentration gradient. So that means even when you have fluid under turbulent conditions, there will be predominantly mass transfer by turbulent diffusion, but the ultimate uniformity, it will be always achieved by molecular diffusion. I hope you are understanding the difference. Then in molecular diffusion, it is not preferred in industrial mass transfer operations, whereas turbulent diffusion, it is always preferred in industrial mass transfer operations. The reason is mass transfer rates are very low in molecular diffusion, whereas you are able to get high mass transfer rates with turbulent diffusion. And for example of molecular diffusion, if a few drops of blue ink are added to a beaker that is containing stagnant water, then uniformity in concentration or uniformity in color, it will be achieved after a very long time. It will take years to have uniform color throughout the beaker. So this is an example of molecular diffusion. Now, if you add a few drops of blue ink to a beaker that is containing water, and if you agitate it, and if agitation is provided, what happens? The uniformity in color, it will be achieved in few seconds. In case of molecular diffusion, it will take years to achieve the final uniformity. But in case of turbulent diffusion, uniformity, it will be achieved within few seconds. So this is how you can compare molecular diffusion with turbulent diffusion. So with this, I complete my discussion on introduction to turbulent diffusion. I hope you have understood what is turbulent diffusion, why it is preferred, what are the limitations of molecular diffusion, and most important, now you will be able to compare molecular diffusion with turbulent diffusion, or you will be able to differentiate between molecular diffusion and turbulent diffusion. So with this, I will end my discussion for part number 1 on mass transfer coefficients. In my next video lecture, I will be discussing F-type mass transfer coefficients. So thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. In my next video, as I said, I will be discussing F-type mass transfer coefficients. For now, have a nice day and hope to see you soon in my next video lecture. Have a nice day. Bye-bye.